In this video, we're going to classify some trig functions as continuous. But in order to do that, we need to learn something called the composite function theorem. Composite functions are functions that are composed together, like one function inside of another. Here we're looking at a composite function where the function g of x has been tucked inside of the function f of x. So our composite is f of x with g of x stuck inside of it. The composite theorem tells us that if we're taking the limit of a composite function, then we can take the limit and sneak it inside of the outside function. So instead of the limit of f of g, we can say evaluate the function f at the limit of g. And if we happen to know what the limit of g is, if it's equal to something like L, then really we're just evaluating the function f at L. So we'd replace the limit with the number L. I'm going to show you why this composite function theorem works, and then we're going to use that to show that the trig functions are continuous. Recall that we've already shown, whoa, typo here, we've already shown that the limit as x approaches 0 for cosine x is equal to 1. And that's actually the same thing as if we had just plugged 0 into cosine x. Now, we did a lot of work to prove this statement, and now it seems kind of trivial. What we're saying is, if you want to know what the limit of cosine x is when x is approaching 0, just plug 0 into cosine, and then you'll find out it's equal to 1. Because that's true, we can say that the function cosine x is continuous at the point x equals 0. So the limit exists, it's equal to the real number 1. The function at that point is equal to 1. Since those two things match, we know that we meet all three conditions for continuity at the point x equals 0. We're going to use this fact, but before we continue, we're going to apply what we just discussed about cosine and the limit as x goes to 0. We're going to apply that to the composite function theorem. So if we wanted to evaluate this limit, where x is approaching pi over 2, the function that we're working with is cosine of x minus pi over 2. Something to note is that we do have a composite of two functions. The outside function is f. That's the cosine x function. The inside function is g. That's the x minus pi over 2 function. To use this composite function theorem, I'm going to sneak the limit inside of the cosine function. So we're going to replace the limit with x approaching pi over 2 of cosine x minus pi over 2. We're going to rewrite that as the limit, there we go, cosine of the limit as x approaches pi over 2. And this time the limit is not of cosine, it's of the inside function, x minus pi over 2. So we moved the outside function outside, and we left the inside function inside where we're applying the limit to that first. Now we're ready to apply the limit, so let's simplify or evaluate the limit. As x approaches pi over 2 of x minus pi over 2, we can just use direct substitution there to get pi over 2 minus pi over 2, which is 0. So then really we're looking at cosine of 0, which we know is equal to 1. Let's try another one. Again, using the composite function theorem, I want to identify what my outside function and my inside function are. The outside function for this second limit is the sine x function. The inside function is x minus pi. To use the composite function theorem, I'm going to sneak that limit symbol inside of the outside function. I'm going to bring the outside function even further out. And then I'm going to apply the limit to the inside function. Using direct substitution here, I can see that that limit is equal to 0. So really, the composite function theorem says evaluate this as sine of 0. We know sine at 0 is equal to 0. Now we're ready to talk about whether or not trig functions are continuous. And to do this, we want to make sure that we're comfortable with the fact that cosine x is continuous at every real number. So we're not just looking at cosine at x equals 0, we're looking at cosine for any value of x. Now we're going to look at the continuity of trig functions. And we're going to start by looking at cosine x. In order for cosine x to be continuous everywhere, we need to show that the limit as x approaches some general value a for cosine x, that the limit is equal to the function evaluated at that same number a. And this is for all values of a. So we'll start off by taking the limit x approaches a for cosine x. Very general statement here. And then we're going to do some manipulations to it. So we're going to start by rewriting x. We're going to take x out and replace it with x minus a plus a. So in this expression, we're going to take x out, and we're going to replace it with x minus a, x plus a. I do have a couple extra parentheses here, but it's not changing how that expression would be evaluated, so it's fine. If we're not comfortable with what's going on here, take a second, convince yourself it's true. Minus a plus a, those two things added together equals 0. So we're really looking at x plus 0. And we know adding 0 doesn't change the value of anything, so these two things are equal to each other. All right, so we started off with our limit, and we applied some weird manipulation to it. The reason why we did that is because there's the thing called the identity for the cosine of the sum of two angles. You should have seen that in a trig class. If this is not familiar to you, I would recommend giving that a quick Goog. Check to see if you remember it. But basically it says if you're taking cosine of two angles, so here we have created two separate angles. One of the angles is x minus a. The other angle is a. If you are taking the cosine of two angles that are being added together, then you can rewrite that expression using this cosine sum of two angles formula. So we have our a angle, and then we also have the x minus a angle. So that cosine formula says if you have the cosine of angle A plus angle B, that's the same thing as cosine A times cosine B minus sine A times sine B. So we used that identity to rewrite, yet again, the expression that we're trying to find the limit of. The reason why we did that is so that we can use the composite theorem. We do have composite functions going on here. We have a composite right here, and we have a composite right here. The outside function is cosine x, and this first time the inside is x minus a. And for the second composite, the outside function is sine x, and the inside is x minus a. Because we have composites, we can use the composite theorem to sneak the limit inside of those composites. So we've moved the limit into the inner part of this composite. And now we're going to use the fact that those limits, where x is approaching a for x minus a, those are the same in both spots. Those each are equal to 0. And since cosine and sine are continuous at 0, we can evaluate cosine at 0. We can evaluate sine at 0. Now we just need to simplify. We know cosine at 0 is equal to 1. Sine at 0 is equal to 0. So we replace those with their values. And then we simplify yet again. 1 times cosine A is just cosine A. 0 times sine A is 0. So our final expression comes out to be cosine A. And although that was a bit lengthy, hopefully you remember that that was our goal. We wanted to start with the limit as x approaches a of cosine x, and we wanted to end at cosine a, and that's exactly what we did. We started with our limit, we applied logical changes to each of these expressions, and we arrived at the final version, which says we can evaluate cosine at a. Notice that we totally used that composite theorem in order to prove this, which is why we started by talking about that and then moved on to this.